Hi everyone, my name is Joel and I'm a senior at Purdue University studying biological engineering. I'm an undergraduate researcher with the Purdue Data Mine and I'm working alongside the Lawrence Livermore National Lab. Welcome to this tutorial on training a production model using AMPL, the Atom Modeling Pipeline. In this session, we'll go step by step through taking a model that's already been trained with optimized hyperparameters and retraining it on the full dataset. This process is what we call creating a production model, which is basically a model that's ready to be shared with others for real-world predictions. A production model is a finalized version of a machine learning model designed to perform predictions on unseen data reliably and efficiently. It's typically deployed into a system or application where it can serve live predictions or automated decision-making. Production models are essential because they bridge the gap between experimental research and practical application, ensuring that insights derived from the data can be utilized effectively in real-world scenarios. Production models are widely used in various domains, such as fraud detection in financial transactions, personalized recommendations in e-commerce, and predictive maintenance in manufacturing. To give you some background, this tutorial is based on the best performing hyperparameters from an earlier tutorial where we compared models to find the best parameters. Here, we're going to use those same parameters but train on the entire dataset, not just the training subset. This allows us to create a stronger, more generalizable model. We'll even compare this production model to the original so we can see how well it performs. So normally, for a scaffold or random split, the dataset is divided into training data, validation data, and test data, with 80%, 10%, and 10% split among these three sections. These numbers are generalizable and they can vary. However, in a production model, the training data is the entire dataset. Think of it this way. If you've only been training on part of the data, you may have missed some patterns. By training on everything, you're giving the model the best chance to learn as much as possible. There are also other methods for creating a production model. For example, you can combine the training and validation subsets while leaving the test subset out for evaluation. Some projects use k-fold cross-validation, which is another way to make sure the model is exposed to different data splits. We won't go into that here, but know it's a good option. To help us along, we'll focus on a few key AMPL functions that are going to make retraining easy and manageable. First, let's take a look at create prediction pipeline from file. This function lets us take a model we've already trained and set it up so we can make predictions on new datasets without needing to train again. Here's how it works. Create prediction pipeline from file builds what's called a model pipeline. Think of this as a kind of object that's ready to make predictions. All we need to do is give this the file path for our saved model. Let's talk about another important function, train model from tar. This function helps us retrain a model that's been stored as a tar.gz file. In AMPL, many models are saved as compressed archives, and this function is perfect for loading those models back up and retraining them. Alright, let's get started by importing the necessary packages. These libraries are going to give us all the tools we need for handling data, building models, making predictions, and even plotting results. First up, we have pandas and OS. Pandas is a popular Python library for handling data in tables or data frames, which is how we'll organize our data throughout this tutorial. OS helps us work with file paths and manage files and folders in our system, making it easier to load and save our models. Next, we have a group of packages specific to AMPL, starting with model retrain and model version utils. These come from ATOMScience-org utils and provide functions for retraining and managing different versions of our models, essential for creating a reliable production model. We're also bringing in model pipeline from ATOMScience-org pipeline. This is our main tool for building, training, and evaluating models. Predict from model will help us make predictions with a production model, and perfplots provides tools to visualize performance of our model. For evaluating model performance, we'll use R-squared score from sklearn metrics. This will allow us to check how well our model predictions align with the actual values. And for math and plotting, we have NumPy for number crunching and matplotlib for creating visuals. We'll use these to visualize our data and results. To get a better view of these packages, you can see them split into 4 categories: data handling, model management, prediction and evaluation, and visualization. If you ever want to use this as a reference to understand what these packages are from, you can utilize this graphic. Now, you might see a couple warnings pop up here. Don't worry, these are just notifications from the library and won't affect what we're doing here. One tells us that AMPL won't be using a model tracker client because it's unsupported in this environment. Instead, models will be saved directly into the file system. So no worries, this just means the models will be saved locally on our computer, which works fine for what we're doing. Finally, we're using filter warnings to suppress some future warnings. Future warnings are heads-up messages about possible changes in future library versions so we can hide them for a cleaner experience. We're starting with our top performing model from tutorial 6, a random forest model that gave us the best result on our validation set. This model achieved an R-squared score of 0.559 on our validation data and was configured using specific parameters for a random forest, including RF estimators, RF max depth, and RF max features. Now before reloading the model, we need to check the AMPL version used to create it is compatible with the version we have installed. Incompatible versions can cause issues with create prediction pipeline from file function, which is how we'll use to load the model. So the installed AMPL version displays the current installed version, and the model AMPL version shows the AMPL version when this model was first created. We're now ready to load our saved model and check its initial parameters. Since this model was trained with validation and test data splits, it was set up with production mode disabled. For production models, we want to change this, but first let's verify the current setting. The output should show that the original parameters production is set to false. This confirms that the model was originally trained with production set to false, which means it was using separate data splits. Later, when retraining, we'll set it to production to true to use all the available data for the production model. Next, we'll go ahead and modify the setup to retrain our model with all the available data. First, we'll specify an output directory to store this new production model. Then, using the train model from tar function with production equal to true, we'll ensure that the model is trained on all the available data without any splitting. After retraining, we'll check the production parameter to ensure it's been set to true and confirm that the model was created with the correct AMPL version. You should see output similar to the following. Production params production is true. This confirms that the model is now set for production. Production model params model tarball path displays the path where the new production model has been saved. And the production model AMPL version ensures compatibility with the AMPL version used to create this model and the installed version. Now, let's evaluate the production model's generalization performance on an independent test dataset. This external dataset is made up of compounds structurally different from those used in training, ensuring that none have a Tanimoto distance lower than 0.4 compared to any compound in the original training set. This will help us assess how well both the original best model and the production model handle new, diverse data. Here we see a preview of the external dataset, including compound identifiers, small strings for molecular structures, and the average pKi value. First, let's predict the pKi values using the original best model. This model was chosen based on its performance on the initial validation dataset. These predictions include both the actual and predicted pKi values with a standard estimate for each prediction. Now let's perform predictions on the same dataset using the production model. Since this model has been retrained on the entire dataset, it may show some difference in performance. The production model predictions also include actual pKi value, predicted pKi, and the predicted standard deviations. Now let's calculate and compare the performance scores of both models. To quantitatively compare these models, we'll calculate the R-squared score for each. A higher R-squared score indicates a better fit between predicted and actual values. The production model achieved a slightly higher R-squared score compared to the original best model, suggesting a marginal improvement in predictive accuracy. While both scores are modest, the production model shows more consistency. Let's plot the predicted versus actual pKi values for both models to visualize their performance. The data points should cluster along the diagonal, indicating a close agreement with the predicted and actual values. Although the R-squared scores aren't that high, the production model on the right over here shows a tighter clustering along the diagonal, which indicates better alignment with the actual values. The production model's slight edge in performance reflects its broader training base, incorporating more structural diversity. Since the test dataset contains compounds with high structural novelty, these results highlight the challenges of creating models with a wide applicability domain in chemistry. To further improve performance, alternative modeling strategies or more extensive hyperparameter optimization could be considered. Production mode, particularly in neural networks, allows the model to train for the best epoch identified in prior non-production training. This approach helps overfitting and maintains model robustness while using optimized hyperparameters and epochs while maximizing data usage. When working with the expanded or updated data, it's often a good idea to train from scratch with a new hyperparameter optimization run. This way, the model can find any new patterns that weren't there before, and we avoid simply patching up the old model. Once the model is retrained, we're ready to share it with other researchers to make predictions on new data. And that's what makes it a true production model. Thank you for watching.